This will be Professor Dr. Dolphy Gilpin as we continue with our quantum mechanics here. And by this time, QM equals and by this time we would have already reached into the J building of City College in the J Science building doing our pre-engineering and pre-med courses, and this was where we had the Schrodinger equation in Chem 103 and Chem 108, also in physics. So we're doing basically science. And then afterwards in engineering, we have these science equations being applied in engineering towards advanced engineering and grad engineering with these quantum mechanics equations. But let's look now at the Schrodinger time-dependent equation. So SCHRO, and we have a 2 dot there. Time-dependent equation. And what we have here is that minus h squared over 2m. Usually h is Planck constant, but I don't know what, let me see what it is defined as here. And m is mass, is partial square by partial x squared, x of t, plus now the potential energy, x of t, psi, x of t, 7.4.5 reference. And this is equal now to h squared partial psi of x and t over partial t. And this is equal now to I is usually square root of -1 here, so that we're going into some complex function here. Partial psi of x and t by partial t. Now, as described by the potential energy the force of the particle described the potential by the equation where U is given by F is equal now to partial potential energy x of t by partial x. For those to a reference to the equation there. And this equation plays a role in quantum mechanics. Similar to Newtonian second law in classical mechanics. So we have some comparison here now to quantum mechanics and Newton's classical mechanics. So this is similar to Newton's second law in classical mechanics. There is some force field here. So I'm going to try to get more adequate lighting so that we could do a more clear and concise description. Okay, now let us consider now that U of x and t, and you know U is equal to potential energy equal constant. And for simplicity, we set U naught equals 0. The Schrodinger equation will reduce to the Schrodinger equation, SCH. We have a valid solution now. The valid solution to the equation is now so x and t is equal to A, B, the amplitude, to the I, bracket wave number x minus omega angular t. And we have here omega is the angular frequency. Not surprisingly, we know that the solution contains an imaginary number, which is the square root of I equal the square root of minus 1. And because the differential equation itself contains an imaginary number, quantum mechanics prediction depends only on the psi. The quantum mechanics prediction depends only on the absolute value of the psi. So, absolute value would be positive square. So we have some imaginary number here, square root of minus 1, which is given as I. But quantum mechanics prediction only depend on the psi, the absolute value of this function here. And absolute values are usually just numbers independent of the minus sign, which yields real values. Go back to your absolute values of number using real values there. All right, we'll take up from there. Let's just mark where we are at here. We have solutions a of x of t equal a sine kx minus omega t, and psi of x and t equals a cos k of x minus omega t. So solutions here, yes. Psi x and t equals a sine wave function of x minus the angular frequency of t. And also psi now to solution of x and t equals a cos wave function of x minus omega t, angular frequency and time. And we said here that this does not obey the Schrodinger equation. Alright, so we'll take up from there on our next bout. We are on quantum mechanics. And since quantum mechanics is a relatively difficult subject, I'm going to take off some of the difficulty from you by giving you a coded definition of the quantum mechanics. Yeah, I'm going to give it to you all, people, but I'm going to give it to you all. Remind me to give it to you all the next time. A coded definition that will make life much simpler.